Hey guys, it's Finn. This video I'm going to implement the backpropagation algorithm in Java. I'm going to use the formulas that we have seen in the last video. If you haven't watched that one, you should stop watching this one right now and watch the last video. For implementing, the first thing we need a new method that actually does all the training and learning stuff. So I'm going to make it public. It doesn't return anything, so void, and I'm going to call it train. What we need some input data. So input. We need a target value or a target vector that we want to reach with our output values, and we need our learning rate. I'm going to call this one eta. First thing we have to check is if the input length not equal to our input size, or the target length is not equal to our output size. This would mean that, for example, the input data that we are trying to feed forward does not have the right dimension or does not the right size. So, for example, our network has 10 input neurons. We're only trying to give 5 input data stuff or whatever. So, in this case, we would return nothing. So nothing happens. Otherwise, what we're doing first, we're going to calculate the output of our network, but we don't need the output right now. The only thing we need is feed the input forward so that each output of each neuron is calculated. The next thing we have to do is we need a new method. And in the last video we did the backpropagation of the error, and then we did the weights update, and we are going to do the same here and split it into two halves. So the first thing is the backpropagation of the error, and for this I'm going to make a new method, and I'm going to call it backprop error, and it needs the target values. So if you look at the formula in the bottom right, you see that if there's a formula for the neurons in the output layer and neurons in the hidden layer. So I'm going to start with the output neurons, and I'm going to make a for loop and loop through all the output neurons. So for int neuron equals 0, neuron smaller than network layer sizes at network size -1. So each output neuron is increased by 1 each time. And if you look at the formula, you see that we need to store the error signals for each neuron. And for doing this, we need to create a new array. And I'm going to call it error signals. And I have to initialize this one like error signals. Oh no, just error signal. And it's pretty much the same as the output array. It has the exact same dimensions. I'm just going to quickly do this one. So here, just copy this, and we got a new error signal array with the same dimensions as our output array. And then we want to set the error signal at our last layer. So error signal at our last layer, that's network size -1 of our current neuron, is equal to the current output minus the target value. So output at network size -1, so our current layer, and the current neuron minus the target value of our current neuron. And we need the derivative of our sigmoid function. We could just write the output times 1 minus output, like we did here. So this thing times 1 minus output. But I think it's more efficient or better to calculate the derivative when we do the feed forward process. So for this I'm going to make a new array again. It has again the same dimensions as our output array. I'm going to call it output derivative. And I'm going to copy this one again. This like this. So we got the output derivative array, same dimensions as the output and the error signal array. This is because each neon has one output, one error signal, and one output derivative. This is kind of obvious, I think. Then the output derivative is equal to the output times 1 minus the output. Oh, not like this, like this. Output times 1 minus output. I'm sure I'm missing something, but oh yeah, at layer neon. So we are not only storing the sigmoid function of each. We are not only using the sigmoid function, we are also using the derivative of the sigmoid function. So in here we are able to use the derivative. We're just calling output derivative at our current at the last layer, so network size -1, and our current neon. I'm going to move this into the next row, and yeah, this is actually it for the output neons. Then I'm going to do the same for or I'm going to apply the formulas for the hidden neons now. But the important thing is that we must go from back to front. So we need to start in the last hidden layer, go to the first hidden layer. So I'm going to start. I'm going to make a for loop, and the int layer is equal to network size -2, because that's the index of the last hidden layer. Then layer must always be greater than 0, because index 0 is input layer, and the first hidden layer is index 1, and layer will be reduced each time. The derivative can be calculated. The error signal can be calculated by taking the output derivative times the sum over the wakes times the following error signals. So I'm going to the first thing is I need to go through every neon in that layer equals 0. I'm just going to copy this quickly. At our layer, and neon increased as well. So now we're going through each neon in each layer, but the layer from back to front. Then I need a sum. So this is a sum over the wakes times their error signals, and this is equal to 0 at the beginning. Then I have to go through every neon in the next layer where we already calculated our error signal. So for int next neon equals 0, next neon smaller than network layer sizes at layer +1, so in the next layer, and next neon is increased as well. Then we want to increase our sum by the connected wake. We want to increase the sum by the wake that connects the next neon and our current neon, and this is the wake at layer +1, because you need to think different now. Like it's not that the neon is connected to the next neon, it's more than the next neon is connected to the neon. So the layer of the next neon is layer +1, and in the feed forward process we had like when we access a wake, we say like, okay, the first thing is the layer, the second index is the neon in that layer, and the third index is the neon in the previous layer. So we need to set when we access this one, we need to set layer +1, not layer, because we are going from the next neon to the neon. Then we got the next neon as the next neon, and then we have the connection to the neon, and this is multiplied by the error signal at layer +1 again of our next neon. Then we can set the error signal of the neon that we're currently working with. So in our layer of our neon, like this. So this dot error signal at layer at neon is equal to the sum, and then we need the derivative again, so output derivative at layer and neon. And that's already it for the backpropagation. Now we need to update the wake, so I'm going to plug this in here, so backprop error of our target value. And the next thing we need to do is we need to change the wakes. The good thing is there are different formulas for the hidden and the output neons, but actually there is no difference, because the only difference is made by the error signal of each neon. So the only thing we need to do now is for each wake that connects, let's say we got neon I and neon J, and the wake connects neon I and neon J. We need to take the output of neon I times the learning rate times the error signal of node J, and we can subtract that from the current wake, and this is how we are going to update each wake. It doesn't matter if we are going from front to back or from back to front. So I'm going to make a new method for that, and I'll call it update wakes, and it needs to know the learning rate. And I'm going to start from at the front. I'm going to the back, but I'm going to start in the first hidden layer, because we are always updating the wakes from a layer to the previous layer. So for int layer equals 1 layer smaller than network size, and layer increased by 1 each time. So we're starting at the first hidden layer and going until we reach network size -1, so the output layer. Then we want to go through every neon, so for int neon equals 0, neon smaller than network layer sizes at layer, and this is increased as well. And then we need to go through every neon in the previous layer to get each wake. So we want to iterate through every wake that connects the current neon to the previous neons. So for int pref neons equals 0 pref neon smaller than network layer sizes at layer -1, so we're talking about the previous layer, and this will be increased by 1 each time. Then the current wake that we're dealing with, I'm going to make a little note here. So the wake that we're dealing with is the wake in our current layer of our current neon connected to the previous neon. And for updating this, we need our delta, and the double delta, if you look at the formula, looks something like this. So we got delta is equal to the negative of eta times the output of the previous layer, so of the previous neon, and this is in the layer -1 of the previous neon, and this needs to be multiplied by the error signal of the current neon, so the error signal in our layer of our neon, and then we can add this value to our current wake. So wake at layer neon and previous neon is increased by delta. This only works for updating the wakes. We cannot directly apply this to the bias. We talked about the bias, and you can understand pretty much the bias is a wake, but the thing is, the bias is not connected to any previous neons, so there's no output of any previous neon. Thing is, the easy thing is that you can just say that that there might be a previous neon with a standardized output of 1. This makes it very easy, and we can just cancel this one out for our bias. So I'm going out of the for loop, because this is for each wake connected to the previous neons or to the previous layer, but each neon only has one bias, and so each neon has multiple neons. Each neon has multiple wakes, but only one bias. So I can jump out of the for loop, and I'm going to make a delta value again, and this looks the same, except we do not have the output thing. So we can just cancel this one out and increase the bias of our current layer, of our current neuron, by the delta value. And this is it for updating the weights. And if we plug this one in, we're giving the eta, and if we plug this in, this train method could actually work. I'm going to check this out. I already created a new main method, and what I do is I created a network, then I made the input, some random values, and I gave him a target output value. So I want the output to change to these values. Then I'm running a for loop 1,000 times, and I'm training the input data, giving the target value and the learning rate. And after I trained my network 1,000 times, I'm feeding the input data forward again, and I'm displaying the output data. And hopefully, this is the same as my target value. And if I do this, this did work. Like, it's not 0, 1, 1, 0, 1, 0, 0, because it's nearly impossible to reach that. Like, the value will never be our target value. And if, for example, if we would increase our eta, we might be closer to what we want. So we have gotten a little bit closer. If we would have more iterations, we might also get closer. And yeah, this gets really good. We can run it 100,000 times maybe, and this nearly gets 0. This nearly gets 1, 0, 0, and this is the learning process implemented in Java. I have one little improvement. So you see that this delta thing is pretty much calculated a lot of times over and over again, and we can calculate the bias before we do the weights calculations, and the delta is the same. So it already delta, I'm going to call it delta weight. So delta weight, and this is equal to the I'm going to make it a little bit easier to see. So this delta is pretty much equal to the delta weight, except we already also got the output of the previous neuron. And if we would remove this one here to the end, and use the delta instead, this would we have less calculations. It's just like a little improvement, and we could this variable is never used really, just added to the weights array. We could just do this directly, so we can add this directly, remove this one, and if I run this again, there shouldn't be any difference, I think. And yeah, and it still works. And in the next video, I'm going to deal with multiple input and target values. So not only one input and output array, but multiple input and output sets. And I hope to see you in the next video.